Going off of the OR 3800 Day 1 handout, read up to example 1, and we will develop a mathematical model for example 1 using the steps above. So step 1 is to determine the objective. In this problem, our objective is to maximize revenue. Next, we want to figure out our decision variables. This is often the toughest part of these problems. When thinking about what our decision variables are in any problem, use these general guidelines to help you figure that out. In example 1, the things that we have control over, or that we as managers can decide, the number of bowls and vases to make. We're developing a mathematical model, and these are variables. So I'm going to be a little bit more specific and say a variable x and y is equal to number of vases to make per week. Okay, so I have two variables, x and y. Step 3 is to determine the objective function. My objective is to maximize revenue, and now I have these variables. So I want to make a function for revenue. Well, revenue equals $50 for every bowl that we make, $40 for every vase. Step 4 is to define the constraints. What are the limitations that we have on our resources in this problem? Read through this problem and you'll find I have constraints on my labor hours. In mathematical form, 3 hours of labor for a bowl, 2 hours of labor for a vase. Total must be less than or equal to 20 hours available per week. 20 hours available each week. I also have a constraint on my clay pounds available. Takes 2 pounds of clay for each bowl produced, 5 pounds for each vase. That must be less than or equal to what I have available, 35 pounds of clay per week. Every problem we do in this class will also have a constraint for non-negativity. That just means that my x and my y variables, or my decision variables, must be positive, must be greater than or equal to 0. We can't make negative number of bowls or a negative number of vases. This constraint will be in every single problem that my decision variables must be greater than or equal to 0. So now we have to figure out what x and y will solve all of these constraints and give us the biggest value for revenue. Looking at the equations, it looks like a headache. We could do this by hand, but in this class we're going to focus on using Excel to solve the problems for us. Now open up the Helen Holmes partial Excel file on Canvas, and we're going to solve that same problem, this time using Excel to do the work for us. This is how we'll solve every problem in this course. Here I have some of the information partially laid out in the spreadsheet. Information about the labor hours in clay pounds for each bowl and vase. Also the revenue for each. This is a formatting thing that we'll do in this course. Any data that I get from the problem, I'm going to highlight in gray and outline in blue. Just like that. This tells me that it's just numbers, there's no formula behind that cell, just a piece of data. My objective is to maximize revenue. My second step in developing a mathematical model is to figure out my decision variables. We did that in the algebraic solution, but I'm going to type it now. My decision variables are the number of bowls and vases to make each week. Okay. This is my x, and this cell is my y. X and y. I'm going to leave them blank though for now. However, I will format them to be decision variables. And how we format cells in this course for decision variables is by outlining them in a dark red border. Okay. So these are my decision variables, x and y. Now I want to make my constraints and my objective function. My objective is to maximize revenue, so now I create a function for revenue. Two ways we can do this. If I look at my algebraic solution, my revenue function was just 50 times the number of bowls produced plus $40 times the number of vases produced. That's one way to do it. Or in this course, we'll use this formula quite a bit in Excel. It's called sum product. And it is the exact same thing as I was doing in the cell above. It's going to take my numbers in one array, highlight my revenue array, put a comma. It's going to sum product them together to another array. Now choose my decision variables. Okay. So for instance, if I sell one bowl and one vase, both are correctly calculating my revenue to be $90. We just need one for one objective cell. I format my objective cell with a double outlined border. Okay. Finally, my constraints. I have some constraints about my labor hours per week and my clay pounds available per week. I'm going to compare for both of those what I actually used and compare that to what's available. From the problem, I know I have 20 labor hours available per week and 35 clay pounds available per week. That's just data that I got from the problem, so I will format it like that. What I actually use must be less than or equal to what's available. That's true for both constraints. Now I need to calculate my actual usage of labor hours. Again, we can do this two ways. I can do it kind of the long way by taking the number of labor hours for a bowl times the number of bowls produced plus 2 hours for a vase times the number of vases produced. Or much faster, I can just use sum product. Clay pounds for each product times the number of products I'm producing. So I have my mathematical model plugged into Excel. It's programmed into Excel. Now, we're going to use a special add-in in Excel called Solver, but we first need to add it in. So follow along as I go up to File, Options, and Add-ins. At the bottom, I want to manage what add-ins I have, so click Go. And then just make sure that your Solver add-in, there's a check by it. Go up to your Data tab at the top of Excel, and you should have a Solver button now. This Solver will find the best X and Y value to give us the biggest revenue. Okay, I can play around and put in different values. Okay, but that would take a long time and a lot of guessing and checking, and I can't meet my constraints. So instead of guessing and checking, let's use Solver. This is the window that Solver brings up, and it asks set the objective. I know my objective is this revenue cell here. So select your revenue cell, and you want to maximize that. That's default, so go ahead and leave it on. But sometimes we will also minimize something. For now, we're maximizing revenue. By changing variable cells, this is what Solver is calling our decision variables. Okay, changing variables, decision variables, same thing. So put your cursor in there and select both of your X and Y, numbers of bowls and vases. Then subject to the constraints, we're going to add some constraints. I want to make this cell less than or equal. There's a drop down, but just leave it as the default less than or equal to for now, to 20, or the cell that has the maximal available in it, and add that constraint. Same thing for the clay pounds, less than or equal to 35. Just like in our algebraic solution, we also had to constrain my x and my y variables to be positive or greater than 0. To add that constraint, we're just going to check this box, make unconstrained variables non-negative. That's just going to make sure that the number of bowls and vases I produce is positive. Finally, we're going to select a solving method. Default is this GRG nonlinear, but this course is all about linear programming. It's called the simplex linear programming method, so LP stands for linear programming. We're going to select this method. That means all of my functions and formulas in Excel are linear, or if I were to graph them on a plane, they would be straight lines. Select that option and click Solve. This says Solver found a solution. All constraints and optimality conditions are satisfied. Click OK, and then now we see a solution. My revenue is maximized, 373. My answer is in decimal form, so which is okay. In reality, we can't make 2.7 bowls or 5.9 vases, but as we progress through the course, we'll add some constraints to make sure this doesn't happen. But for now, this is a good enough solution for an intro example to make 2.72 bowls, 5.9 vases per week to achieve a revenue of 373.